Hi, my name is Christoph Randrup. Thanks for joining. If you have any questions during the speech, just interrupt me and I will answer. Just a bit about my background. I worked 4 years at Silicon Graphics on site at BMW, taking care of their virtual reality centers, virtual reality software. After that, I switched to Audi, worked in their central IT department, being responsible for the design and ergonomics department. And beginning of 2009, I joined Autodesk Consulting. So I have some visualization background. What this class is about, it's about photorealistic images. You all know they are needed to speed up design decisions. They are needed for marketing purposes. And quite often you want them next day, but it takes hours and hours and hours. So this class is about how can I speed up my rendering with different techniques. This is just a real-life example. We rendered 27,000 frames, and that will take 1,200 days if you render those in the resolution that was wanted and with the quality that was wanted. And then we used 320 nodes, and we did the same job in just 4 days. At the end of this class, you will know how to set up a thread scene, as in real-life example, how we did it for large render jobs, how to set up a cluster in a cloud environment, in a private cloud with a scheduling system, best practices on compute time, price and performance, as Thread is an online tool, how have we managed to get the jobs rendered and get them rendered unattended. And the last slides will show how a major German automotive uses the rendered images for reaching design decisions. If you set up Thread to render jobs, you of course need to set views, cameras for still images. You need to set animations if you want to render a movie. Then you choose the relevant variants if you want it high class or which colors and those things. You define the level of quality that you want to reach, if it's for big posters or if it's just for your daily talks. You set the resolution and the different auxiliary and illumination channels if you need them for post. As an example, those channels can be the indirect lighting, the direct lighting, and so on. So you choose all this, and to make this, you make use of the thread sequencer. This is the thread sequencer. So imagine your scene is ready, everything is set up, and then you want to define what needs to be rendered. You open the sequencer, and then you just say, okay, animation drive, you set the render mode, it's in ray tracing, how many samples do you want, you select a variant, in this case highline, and then you choose the size of the movie, in this case for the animation, the start and the stop frame. So all is set up in the sequencer, and more actions can be added. So all you can do by mouse, if you say render image and then select, can be predefined in the sequencer. And then we tell Thread afterwards, simply start going through the sequencer and process the jobs. That's how it works. In our case, we switch to ray tracing, we define the samples, we select a variant, and then we choose some auxiliary channels and render a movie. The example here below is the same for just create a snapshot. And there are actions for most of the things that you want to define. If we do that unattended, means you start Thread and you don't know when it starts. It starts during night, the computer starts the job. Then, of course, you need to define somehow where the images should be stored afterwards. because in our case, the thread designers hand over the scenes to the IT department, and then the IT department starts rendering those things and puts it into the scheduling system. And that's why we simply read an environment variable that is defined by the scheduling system so that they know where the images are stored. Because the thread designer doesn't know where the images should be stored. And that's why we define the target directory where the frames should be stored. A bit about how thread works in general and how the cluster works in general. We have a cluster master. This is the machine there on the top. This is the machine that loads the thread scene, distributes the scene to all those slaves, and saves the result. So when the rendering starts, regardless if it's real-time rendering or if it's offline rendering, our master sends the complete scene to all the slaves, and then those slaves send back the tiles they are responsible for. The top image you see this grid, and each square is a tile. So for example, this machine renders one tile of the headlamp, the next machine renders the other tile of the headlamp, and then they send back the tiles, the master combines them, and then we have got the final image. So that's how the thread clustering works. Of course, you can define the tile size. So if you say normal tile size is 32 by 32 pixels, but you can reduce it to 8 by 8 pixels, make it larger or smaller, whatever you want. This is how a general cluster setup is done and working. Two ways we did in the past as real-life examples. On the one hand, we used the Amazon Cloud. The advantage of the Amazon Cloud, it's easy to access and it's easy to reserve multiple nodes. I create an Amazon account, and then I go there and say, okay, I need 20 machines, I need 40 machines, whatever I want. For renderings I did a 20 node cluster on the Amazon Cloud as an example, and that just cost $20 per hour. So quite cheap. So one node cost $1 per hour, the ones that I used. And if you add more 40 nodes, then you just pay $40 per hour. Another advantage is you have full control of the whole environment and timing. You decide when to start, when to stop, and it's fully up to you. You have the full control. If you use a private cloud or a compute center, that feels more secure for some customers with sensitive data, because an automotive customer in Germany told us, if you upload our data to the Amazon Cloud, you will be in trouble, even if nothing happens. So that's why we went to a local compute center that is not connected to the internet. It has just lots of compute power, but of course we need to integrate our jobs into their scheduling system, because we can't simply go there and say, hey, there we are, we want to start, and we need 400 nodes, because they are not available. So that's why we integrated it into their scheduling system, that we scheduled those jobs, and then during night one job started, the other one started in the morning, the next one over the afternoon. So all needed to be and to work unattended. And that's the disadvantage if you use a private cloud or a compute center. The advantage, of course, it is more secure, or it feels more secure than the Amazon Cloud. And customers that have large compute centers on their own for their crash calculation, as an example, can use this cluster for renderings, as they have a scheduling system set up for crash calculation anyway. And we use the same nodes like the crash guys use. So the needs are really quite similar. So how is the Amazon Cloud setup done? Those steps are needed. You start your instance. An instance is more or less a machine. So the Amazon Cloud calls one node or one computer an instance. You create a security group. A security group acts as a virtual firewall that secures your nodes. and is responsible for the traffic. It controls the ports. And when you launch an instance, you associate this to a security group. And so you define how secure it is, which ports are opened, which are closed, and so on. You install the software, you create an image, and you restart the whole thing with more powerful instances. I will explain those steps in more detail. So start your instance. You simply go to the Amazon Cloud Management Console. You select an instance and press Launch Instance. Then you are asked at the first time, do you want a Windows? Which type of Windows do you want? Do you want Linux? Whatever. So you have lots of options to choose from. For our case, we just used Windows Server 2012. The micro instance is a really small machine with just 512 megabytes of RAM, but it's for free for the first year, and then it's really cheap. So the setup can be done while you more or less burn no money, because you do the setup, you upload your software and everything by using these micro instances that you know, okay, everything is said and done. And this is more or less for free. I think in the second year you have to pay for the micro instance, but they are really cheap. Then you start it and you do the same for Linux. So what we have now is we have a Windows machine running and a Linux machine running. Both can be accessed from your desktop via remote session. It's easy, and up to now we burned no money. Then we create this security group. Here's just the example for VRED. You add some ports that need to be open. So we define the ports. Those are for the VRED cluster, and the last one is for the license server. And then you apply the security group to all your nodes. So by this, your nodes can talk, and it's secure. Next thing is and this is just a snapshot of the remote desktop connection to such a micro instance. And on a micro instance, the armchair example is running. So don't try to open large files on a micro instance. That will not work, but the armchair is running. You install VRED Pro on your Windows instance and the VRED cluster binaries. It's a smaller piece of software. You install that on your Linux instance. And on the Linux instance, you just make sure that when they boot, the service starts automatically. Because in the next step, we start our Windows machine, and then we want 20 Linux nodes. Okay, that's in between. Then we create an image, because we have installed VRED on the Windows machine. We have installed the cluster binaries on our cluster nodes, and we have created the security group, and everything is fine, but we don't want to redo all of this. So that's why we create an image, and then this image is saved. And next time we boot a machine, we can choose our image, which is called Windows VRED 2015 installed, Linux cluster service installed. And we boot more powerful machines. So here you see we start 10 instances of our Linux image, and by one click we have 10 nodes running. And that's why I said make sure that your service starts automatically, because they boot and then you don't have to log in, you have to do nothing because they are up and running. You choose your AMIs, you launch a Windows instance, you launch as many Linux instances as you want, and then you can start rendering. For a project with a customer, we used Box to transfer the files, so we installed Box on the Windows machine. Then we shared the directory via Box with the customer, so he could see more or less, when the image was done, he had the image. So Box synced all the images, and the customer could easily see, okay, another image rendered, another image rendered, another image rendered. And for us, it was the same. I just started all this on a Friday afternoon, and then I just looked at the box directory, so I didn't have to log in all the time to the Windows machine. Is it still running? Because I saw that images come in. Any questions on the Amazon Cloud setup? Yeah.
Would be any advantage if I use GPU enabled instance? With more GPU power, would be better rendering, faster rendering?
No, because VRED just uses the CPU. It doesn't make sense to use any GPU, powerful GPU nodes. Yeah. So it's only for ray tracing. So if you do OpenGL, it doesn't accelerate anything. It's just for ray tracing. The license server is running on a micro instance. So I set up everything and I let the micro instance running, and there was the license server running, so that the license server didn't change. And then I knew the IP of the license server and simply put that into my image descriptions. So let's say my micro instance has the IP 10.10.10.1. Then I kept that running, the license server was running all the time. And then while I created my instances, I said the ADSK Flex license is at 10.10.10.1. And then I saved it, license server was still running, and when I pushed everything up with more powerful machines, they connected to the correct license server. Yeah. That's maybe the hardest part, the license server in the whole solution, that you need to have this license server running on a micro instance. But as a micro instance is for free, it doesn't add any additional costs. Of course, what you can also do if you have a license server that can be reached from the Amazon Cloud environment, you can use that one as well, because you can open external ports via the security group as well, if your license server is reachable over the Amazon Cloud environment. I think that might be harder than using a micro instance.
Did you have a license just on your local machine or on your local network? Or does it need to be on a computer on Amazon Cloud?
Depends. I mean, if your Amazon Cloud nodes can connect to your local license server, which might be hard, but don't know if that works, then you can use that license server. It just needs to be reachable for the nodes. Yeah.
Regarding licensing, does not include some number of instances that I can connect to the license and work. So the more I need, the more licenses.
Yes, the licensing is you need one VRED Pro and one cluster license for each node. So let's say we had these 10, then you need one VRED Pro and 10 cluster licenses. Yeah. AMI stands for Amazon Machine Image, because I just said always AMI, it's Amazon Machine Image. Okay? Okay. If you have a private compute center in your company, or you have a compute center located next to you, and in this case we use the compute center of a university, we needed to set up an unattended start and stop for the rendering process. So the scheduling system in this case decides when to start and on which resources to start. So we used Sun Grid Engine. Sun Grid Engine was bought by Oracle, but our customers still used Sun Grid Engine, and we included this into the Sun Grid Engine. It works like this, that you start the job, you say, I want 40 nodes, this is the data set, and then you send it to the scheduling system, and then the scheduling system knows, okay, I need 40 nodes, and as soon as they are available, it reserves those 40 nodes and starts the job. That's how it works with the scheduling system. The complete and start and stop mechanism has, of course, to work unattended, because I don't know when it starts and I don't know when the resources are available. And you need to integrate the thread start and the cluster start into your scheduling system. How this is done? Again, the target directory, and then we start the rendering process. The target directory is important as I said, if the designers do the scene setup and everything, you don't know when and where the images should be, so this is decided by the scheduling system or by the administrator. I will explain the parameters a bit more in detail. We just say thread pro minus no GUI minus post Python. That starts thread and executes the following command after the scene is loaded. So here the $scene is the variable for the scene. It can be my armchair.vpb, whatever. Thread starts without a GUI, and then it executes after the scene is loaded the following commands. There is a pre-Python, so this says minus post Python. There is a minus pre-Python option as well, and this option says execute the commands in advance the scene is loaded. That's the difference. Set render quality, we switch to ray tracing mode. This is important because thread starts, it's an OpenGL mode, so we need to tell thread you are in ray tracing mode. Start the ray tracing cluster, and here you see Scratch project nodes.txt. The nodes.txt is simply the file with all the addresses of my nodes. And the scheduling system takes care of these nodes.txt. When the scheduler sees 40 machines are available, it writes the names of all those machines in the nodes.txt file so that thread knows, okay, which nodes can I use and which nodes are available. The other parameters are just if you use direct connect, the tile size, if we use compression, supersampling, and all those things. Of course, we don't use compression because it's just online. And $node_num is just the number of nodes. This is the value for the parallel channels. Then we run all the predefined sequences. When this is done, we stop the cluster because our job is done. And when this is done, we terminate thread. And the scheduling system realizes by the job stopped, the job is done. And then it releases the nodes, and then the next job can start. So the last two commands are really important, that the scheduling system sees, okay, the job is done, I can use those nodes for other jobs. Otherwise, it might happen that your job starts in the morning and you see, oh, it will end 3 o'clock in the morning, and then the nodes might be reserved until you reach the office the next morning. So with this command, it starts completely unattended. You can integrate it into a scheduling system, and when it stops, the resources are free and available again. Any questions on this setup for a private cloud?
So basically, once you stop, you release all the nodes. So if for some reason you needed to stop the job, you couldn't just restart it at a later time. Basically, it's done.
Yeah, yeah. I mean, you put in our case.
You open VRED back up, redesign the frame sequence you want to render, save that off, and then rerun it as a separate job.
Yeah.
Will this work with dynamic nodes? So can you change the number of nodes that are working on it? Can that fluctuate?
In thread, we can't do that yet.
Okay.
So if a cluster is started, and if one node crashes, the whole scene crashes. We can't do that yet. So, yeah, yeah.
And cluster, you can't send out multiple frames to each node, is that correct?
This is a bit harder because we tried that and we still think of sending one frame to one node, but it didn't work for the animations our customer had because they do a lot of tongue mapping as well, and then the images, it didn't work with the version we had. There are plans to integrate VRED with a cube, the cube queuing system, and then it works a bit different. But in our case, one frame per node didn't work. So that's why we said, okay, we need jobs, we need the whole cluster, and run the images one after another and not all in parallel. Yeah. Okay? So integrate the start-stop scripts into the scheduling system. Typically, the jobs we ran, they ran on 40 nodes. So the scheduling system has to reserve those 40 nodes, create the text file so that we afterwards know which nodes were reserved, start the cluster service on all the cluster clients because they are used for crash calculation and other things. And that's why we simply can't have our daemon running all the time. Copy the input scene into the project directory so that it's there and that we can start. And start the VRED script from the chosen master. This can be any master. If 40 nodes are reserved, those 40 nodes are all the same hardware, all the same operating system, and then notify the user when the job is done. We did this on Linux and on Windows. So the command line you see will work on Windows and on Linux. We didn't use a mixed environment. We used mainly Linux, but it will work on a Windows cluster as well. How have we split up the scene? So the VRED scenes are set up to render multiple animations or images. Sequences can be organized to contain one image or animation or multiple images and multiple animations. So you see that in our interior snapshots, you see we set the render quality, set ray tracing image samples, select variants, jump to one viewpoint, and create a snapshot. After that, we select another variant, jump to another viewpoint, and create another snapshot, and so on. And then one cluster renders one of those sequences. So the users do the setup, they set up all the sequences, and then let's say they have 10 sequences, then we made 10 jobs out of it. We made that because running all on one cluster takes a long time, and smaller ones, it's quicker and they can run in parallel. And by selecting the different sequences, the work can be shared. If you just have a small size cluster, you make 10 jobs and then they run. Advantage and disadvantages, you might say, if I have such a large cluster, why don't you simply use 500 nodes, run the complete sequence, and you are done? Because it makes it easier for the scheduler. If you ask a scheduling system to reserve 100 nodes for you, the chances that you get those 100 nodes are not that high if you ask for just 40. Because one job stops, one starts, another one stops. In your whole environment, it's not only VRED jobs. So we realized, and we talked to the IT guys, and they said, if your jobs are smaller, the chances are higher that you get those slots. That's why we split it up. Jobs can run in parallel on a big cluster and sequential on a smaller cluster. So with this setup, it works for smaller clusters, and it works for large clusters as well. The risk of errors is a bit smaller. So let's say you use your 500 nodes clusters, started on a Friday, on a Monday you realize, oh, everything crashed on Saturday morning. then you have nothing, no image. If you run 20 jobs on just small parts of the cluster, and on Monday morning just one crashed, then it's one, and you can easily restart that job. So that's a big advantage if you just think of running on a large or on a small cluster. And we saw, because you ask, why don't you render one frame on one node? Because that might be or is the perfect scaling solution, of course. And we saw that with larger jobs, of course we scale, but we don't scale linear up to 500 nodes. At a certain point, our curve goes just like this. And of course, our customer said, I pay for compute hours. And if I lose money, and if the job runs longer on 500 nodes, if I split it up in 10 jobs, each running on 50 nodes, and then you compare the time, and the time of the 500 nodes might be longer, total time, they waste money. So another reason for that is that if we would scale linear to 500 nodes, okay, but as we don't, splitting it up in jobs for 40 nodes was a real good solution. Any questions on the scheduling mechanism? No? Okay. Then I will switch to a real-life example. This is an example where a customer used those 27,000 frames for and still uses it for. The Russian arm car is a car where a camera and an arm is mounted on the roof of that car. The driver is driving the car, and next to the driver sits the camera guy, and he remote controls the camera on the top. This is a real fast Mercedes, and they were driving on the highway and everything, so they go really fast, and while driving, the cameraman can rotate the camera, can look at any angle, and so on. So the first step was, this customer wanted to show his cars in real-life examples. So see your future designs, driving on the highway, parking in the parking lot, driving in the city. So see the cars in an environment that is common and that is known. So they filmed and scanned a real vehicle with the Russian arm. Lots of scenarios. So a real car was driving in the front, and this car was filmed. And then parts of the environment were modeled in VRED. So what was modeled? The street was modeled, the pavement was modeled, so that afterwards you can match it to your virtual world. And the car, of course, was hidden. The real car was hidden. Then you use the film content as background. So let's say somebody is walking by and you see the reflection of the pedestrian in the car. You want to see this in the movie you render afterwards as well. So frame by frame, you use the film content as a background. Yep.
Can you actually stream the video into VRED, or do you have to do it frame?
Yeah. They set up an automated pipeline that understands the input so that it knows, okay, this frame, this frame, this frame, this frame. Because another thing you need to do, you of course need to have an animation that perfectly fits to the drive. And it's this Russian arm car, it scans the environment as well. So you get a point cloud. You don't get just the movie. And yeah, you have the positions. And by this, you know you can do an animation. And by the position, you know which background image do I need now, and now, and now, and now.
So you can pipe in all those camera positions.
Yeah.
And then use that as your animation.
Yeah. So that's the first step. And then the second step is you render and combine. This is your car, your virtual car that you want to have placed in the rendered environment and have the movie. So you render the virtual car animation by using sequences, one image per frame, render passes for the different channels, and afterwards you have lots of images like the top one. And if you just go through it, you see the car driving, like the real car was driving, and then you combine this, and afterwards you have a real movie. The setup is done that right now they have lots of films defined. So once you have them, now it's easy. A new car comes in, then I simply put it in my VRED scene, start the rendering, and the movie comes out. Unfortunately, I can't show a movie because the plan was that I do this presentation with the customer, but the customer couldn't come. So that's why I can't show a movie of how this was done. Done already. Thanks for listening. And hopefully next year the customer will be with me.